Unit 2. Okay. So today we're going to talk about linear approximation and differentials, which really is going to feel like the same thing. Okay. Um, Anytime you see linear approximation or the linearization, it means, hey, use the tangent line to approximate. Okay, because a tangent line is linear. Okay, and tangent lines are easy to do approximations with. Okay, plugging 4.02 into like a quadratic, not a lot of fun if you don't have your calculator, right? Okay. So what we're going to do today is we're going to approximate using our knowledge of tangent lines. Okay, so the first thing, linear approximation, we're literally going to write the equation of a tangent line and use it to approximate a value. Okay, so here is our red curve. Okay, here is our tangent line. Okay, if this was where x is 5.79, okay, that's not going to be nice to plug in if we don't have a calculator. But if we can plug in 5.79 to our tangent line, okay, we know it's not exact, but it's pretty close to the approximation. Okay. So this right here is just kind of the steps that we're going to take, right? So let's remember how to write the equation of a tangent line. Yes?
So plugging in that point gives you your y value?
Well, it's going to approximate our y value, right? So if we plug in that x value here, it's going to give us a y value that's close to the actual function value.
And what is it really that much easier plugging it into the derivative? Because sometimes you can get like long, complicated ones.
I will show you. Okay. So let's remember how to write the equation of a tangent line. So I'll revisit that question here pretty soon. Okay. So we take the derivative, and that tells us our slope, right? And then we use point slope form. Y minus y equals slope times x minus x, right? And then our slope is really our derivative. Okay. And then if we're approximating the y value, we're going to have to add this number over. Okay. So that's what I have right here. That's all that this is. Okay. So what we're going to do is we're going to approximate the square root of something. Okay. So the first thing we're going to do is we're going to write the tangent line at x equals 4 to the square root of x. So what do we need to do first? Find the derivative, and what is the derivative?
1 over x2.
Okay, good. And so what is the derivative evaluated at 4? 4. Okay. So we have slope. Do we have a point? What is our point?
2, 4, or 4, 2.
We have the point 4, 2, right?
Plug 4 in the
Square root of 4. Well, to write a line, we need a point and we need slope. So we had slope. Now we need our coordinate.
So you just plug in x value?
Yes. Yes. So here's our tangent line, right? Okay. Now, we're going to use this to approximate something. So what I'm going to go ahead and do is I'm going to add this 2 over. Do you want me to add it to the end instead? Or is it okay right there? Okay. So this is what we call our linearization. Okay, it's our tangent line. Okay, now what we're going to do with that is approximate the square root of 4.02. Okay, without a calculator, do you know what the square root of 4.02 is? It was a nice try. Okay, so what we're going to do, since we don't have a calculator, okay, per se, right, we are going to use the tangent line to approximate this. Okay, so what was our tangent line? Y equals 2 plus 1/4 times x minus 4. Okay, now we use x is 4 because we want to approximate 4.02. So we're not that far off from x is 4, which means our approximation shouldn't be too far off from its actual y value. From 2, thank you. Well, not from 2, but from the actual square root of 4.02. Okay, so what are we going to do?
Plug it in for X.
Okay, plug it in for x. Okay, so what do we have? Well, we don't need the square root because this our function was square root of x, right? And we wrote our tangent line. So since this is square root of 4.02, 4.02 is our x value. Okay, and then we're
function. I thought it was the X value.
what?
The way you put that in, you're saying that you just said that was the X value, but now you're saying that that's the function itself.
Well, our function is square root of x.
Yeah.
Okay. And so 4.02 is where the x is, correct? So 4.02 is what we're plugging in for x to approximate the square root, since our function is the square root of x. Okay. So what do we get here?
102.
Okay. Or we could write, okay, so 0.02 divided by 4. Okay.
That's pretty cool.
So has your calculator out. Aaron does. Aaron, what is the square root of 4.02? Oh, wait, don't do it yet. Don't do it yet, actually. Before Aaron does it,
I thought we forgot to do
okay. Is this approximation an over or under approximation?
Over.
Why?
Because the number we plugged in is larger than the value of our, than what we're approximating to.
False. True statement, but that's not why it's an over approximation. It's a great idea. Let's think of calculus.
Is it because it's positive?
No.
Well, I guess.
X minus
Because
eight.
it's 2 plus, and then the reason is because it's positive.
Mm-hmm. That's not right. What is true about the concavity? It is concave down. Since we are concave down, what does that mean about our tangent line? It sits above our curve. So, since our tangent line is above our curve, we have an over approximation. If we were concave up, our tangent line would sit underneath, and therefore we have an under approximation because the values on the line are underneath the values on the actual curve. Okay? So, you're right with the over approximation, but it's because of the concavity. If I ever ask you to tell me and justify whether it's an under or over approximation, we're talking about a tangent line, you need to use the concavity. So Aaron, what was the square root of 4.00?
2.0049.
Calculus is amazing.
So when we try to find a second derivative,
It's either that or just know what the function looks like. We know what square root of x looks like. We know that it's concave down. Okay. Okay. So let's talk about differentials because that's really why we're here. Okay.
Wait, so that had nothing to do with differential?
It does. It does. It does. But this is something you've done before, right? Tangent line approximations? I mean, tangent lines, right? Okay. I want you to look at this picture.
Oh, I don't wanna.
good looking, right?
Okay, one number is delta y and delta x.
Okay.
Change your mind, change it.
Okay. Those of you who have, you guys talk about that in physics? Yes. Okay. Delta, when you see it in math, means change in. Okay. So change in x and change in y. Okay. Yes. Okay. So here's our point x, y. Okay. And then here's another point on our curve x, y. Okay. So this is x, y. Change in x over change in y. That is how we get to that new point. The change in x horizontally, how far have we moved horizontally? The change in y, how far have we moved vertically? Okay. Now, when we find the derivative at this point, we're talking about the slope of that specific tangent line. So if we think about rise over run, okay, we have dy, dx. Our rise is dy, our run is dx, right? Our derivative is the slope of that tangent line, right? Okay. So this is what's happening when we do differentials, okay? We're basically going to do what we just did in a little bit more streamlined way, okay? So this point right here, okay, if we call the change in x delta x, then this x value right here is where we started, x plus that change in x. So x plus delta x, right? Okay, now, look here. We have the change in y, and then we have dy. Okay? With a tangent line, which one are we going to be able to know? Dy. Okay? So we're going to use dy and dx and the change in x to help us figure out what our change in y is. We're going to use it to help us approximate. Okay? So I'm going to come back to this picture a couple times probably. Okay? So, things to remember. Delta x is going to be the same thing as dx, which means change in x. Okay? Yeah.
I understand the total delta thing. It's pretty simple, but why not just use h? Like we've always done.
Because we're gonna compare some things with the derivatives, like delta y over delta x.
So then put delta y as like L.
We're gonna use delta y and delta x. Okay? It makes it a little more streamlined. Okay? And maybe when we get to an example, you'll see it a little bit better. Okay. What was I talking about? I was talking about delta y. Delta y is the change in the function value, right? We're on the curve. Okay? Delta y is the actual change in our function from x to delta x. dy is the change in y of the tangent line. So, what are a couple different ways we write derivatives? We write y prime, or we write dy dx, or we write, okay, right? So you agree that dy dx and f prime of x mean the same thing? Okay, so do you agree with me when I say dy equals f prime of x dx?
Yeah.
Just move the dx piece over here. Okay, so if we don't have any change in x, then obviously dy equals delta y. But that's probably not going to happen. That would not be the point of what we're doing. But if there's no change in x, then dy and delta y are the same. Okay. Are you ready? Okay. What? Okay. So, same example, but I'm actually, same example. Okay, so we have the square root of x at x is 4, and our change in x is 0.02. Okay, so what is dx? Okay, cool. Dx and delta x are the same thing. Okay, trick question. No, not a trick question. Okay, dy. What did we say about dy? Okay, so let's talk about f prime of x. We already found f prime of x, didn't we? Okay, so dy is f prime of x, but we're focusing on x is 4. So what is f prime of 4? 1/4 times 0.002. Sorry, too many zeros.
So we're basically just breaking apart our.
Okay, so let's go back to our picture. 0.005 is from C to D. What are we looking for? We're looking from here to here, right? So how could we get that? So what we're doing. We're going to take f of let me write it down, and then we'll go back to the picture. We're going to take f of x plus delta x minus f of x. Okay, this is going to be the actual change in y. So this is something that we're going to have to use our calculator with. What is the square root of 4.02, right? X plus delta x, that would be square root of 4.02 minus the square root of 4. This is something you need your calculator with.
That's finding the exact value.
Yes, this is the exact change. Yeah.
Why are you using a square root of 4.2?
Because our change in x is 0.02.
Okay.
We started at 4.
Plus or x,
Okay.
which is 4.
It's 0.005.
And then 0.0049,
Yeah.
something, right? So close, right? So basically, okay, dy and delta y should be the same thing. Let's talk about what dy is going to tell us. Right. So if we're going to approximate the square root of 4.02, we would say it's approximately what? 0.005. 2.005. Right. Okay. So this is telling us how much different it is from f of x. Yes.
And this will all be non-calculator stuff?
Because I probably would not ask you to do this on the test. It'd be more like this.
Wait, so is that like all we were doing? Like, is that it?
Yes.
Okay, just make sure.
That is it. Yep.
Because the original equation was in y equals 1 x minus 4 plus 2.
Okay,
we basically like found everything the first time we did it, and then we were just labeling.
Okay, so let's do another one. One that we haven't done. Okay. So y equals 4x cubed minus 1. When x is 1, and our change in x is delta x. Okay. So, well, there's delta x is 0.01. So we want dy. And how do we find dy? Okay. So, what is f prime of x? Okay. 12x squared evaluated at 1. Okay. And then times dx. 101. So what's dy? 0.12. This is non-calculator stuff, people. Right? So you're essentially multiplying by 1. That 1, 2 is not going to change. But we're multiplying by 1, 100th, so we have to move the decimal 2 places. Okay? So dy is 0.12. Let's talk about what that means. What is f of 1? 3. So f of 1.01 is approximately 3.12. It's just giving you that change.
Oh, okay.
Okay. So this is it's kind of making it easier than writing the tangent line, right? Yes.
Wait, why did you do all
I don't know.
Okay, so f of 1 is 3, correct?
that? Yes.
Okay, so f of 1.01,
Yeah, why are you doing
that, it's just kind of using dy to put it all together. What does this actually mean? What is that 0.12? Okay, that's just the difference in y value from x to delta, to x plus delta x. So from 1 to 1.01, we changed our y value by this much.
that?
Why don't you just apply a factor of 1 every time?
All right, so we used our slope, right? We used our slope of 12, right, to approximate that y value. Okay. Now, this is nice only if we're doing things close to 1, okay? You would now want to use this to approximate f of 5, right? Or we wouldn't have to approximate that. F of 5.1. You would not want to use this to approximate it. You would want to use, you want x is 5 and do that differential there. Okay? Okay. One more example. Okay. How do you find the volume of a sphere?
Over 3 pi r squared. No, pi r cubed.
Okay. So, we want to know the error in computing the volume of a sphere of radius 10, and we want to be within 0.2 centimeters. Okay. So what's 0.2? Okay. So, maybe instead of delta x, we could call it delta r. Ah, that's a hole. Is that your favorite?
Oh, I missed it.
No. Okay. So, instead of dy, we're going to look for dv. Okay. So dv equals derivative. Okay. What is a derivative? 3 times 4/3 pi r squared. Okay, and then we multiply that by dr. It's just dr instead of dx, dv instead of dy. Okay?
You're in delta are the same.
Yes. Yes. So we have dv equals 4 pi. Now they told us our radius is 10. And we know that delta r, which is the same thing as dr, is 0.2. Keeping it in terms of pi, what do we have here? There's 0.2. And we're talking about volume, right? Do you agree with Zach? No?
Wouldn't it be like 8? 400 is 5.
So 400
Oh, you're
times
adding.
0.2.
No, wait, you're
Yeah.
multiplying by 5.
Aaron, disagree with that.
Alright, I guess you're right.
Okay, so that's how much we are off by. Now, okay, that's all fine and dandy, but what does that mean? Let's calculate the percentage error. Nice people, how do you,
Actual minus.
Minus.
What's the difference between the actual
Actual
and
minus
the
divided by.
the absolute value of that? all over. Actual.
Okay, so actual minus
Estimated
estimated,
minus.
all over actual, right? Okay, so let's talk about it in this case. Well, what's our actual minus
20%.
estimated? Like, what value is actual minus estimated?
10.2 or 9.2.
80.
This is the difference between, right? This is dv or our dy. Picture. Right?
Oh, it's dy minus delta y.
Oh, I
It's dy minus delta y.
I'm good. That's all we need to do.
Yep. Yeah.
How much? We're off by over our volume. Okay, so we have 80 pi over 4/3 pi 10 cubed.
So you just drop off the negative sign?
Well, if we're talking about a percentage error, we wouldn't need to worry about negatives, right?
Why wouldn't you use 10.2 on the bar?
What?
For R, why wouldn't it be 10.2? Because it's the actual.
Because they give you 10 radius. Don't they?
Well, because we're. Hold on. Let me double check. I think we keep it.
What's 86%?
6% because it's 0.067, right?
Yeah, I got 106.
0.06.
It's 4,000 pi, 30 is like 488 something, and then 80 pi, and then that is 0.06.
Okay, so 0.06 what?
Well, it's 6%.
There's nothing after 0.06?
No.
Okay, so our error is plus or minus 0.06. So our percentage error would be 6%.
That's pretty good.
Rather than
Here you go.
Oops.
This is not a lot of problems.
That's his fault.
Wait,
You should go with that. I'm gonna go with that one. I choose that one.
Wait, are we
I
doing
didn't know, I
seven?
just wanted to tell him that I don't have to do that.